to just give some more time for people to join? Sure.
Good.
All right.
Yeah, good.
Cool. Looking sharp, Jay.
Gives me a good reason to dress up. Miss it.
So good afternoon, everyone, and thanks again for joining Structured Technologies in the Strengthening Webinars series. Today marks our final Strengthening webinar. It's unfortunate. We've been conducting these webinars for the past 2 weeks almost. We truly hope that we were able to add value to you, and we also truly hope that we've actually used your time in a valuable way. Today's presentation is titled Conventional Methods or Strengthening Techniques Using Conventional Methods. My name is Karam Salahia, and I will be the moderator for today's session. I'm a business development manager working in our Dubai's office. And again, as a company, our aim from these sets of webinars or series of webinars is to basically empower our clients and share with them some of the experiences and technical knowledge that our subject matter experts have. We're glad to have you on, and as a company, we thought that this is one of the ways that we can actually add to the society or give to the society, considering everything that's happening around with the COVID-19 and everything. Now, before we start, I just wanted to share a couple of housekeeping items with you. All of the audience members are muted during the call. However, you may ask questions. If you wave your mouse to the bottom tab, there's a Q&A tab. I would politely ask you to actually put your questions in the Q&A tab and not in the chat function. At the end of the presentation and also during the presentation, Jay will be answering some of the questions. Unfortunately, sometimes we get a lot of questions that by the time we end up the presentation, we don't have time to answer all of these questions. So if this happens, please feel free to email your questions to me or to James or to Jay directly, and we'll make sure to basically address them and get back to you in due time. Now, if you have selected that you needed a certificate of attendance, please note that you will be getting one in the second week of May. And as always, we as a company truly take your feedback into consideration, and we are always working on improving the content or the webinars that we give. So by the end of this webinar, there will be a short survey that will take literally 1 minute out of your time. We truly appreciate if you can fill that out. Jay, can you move to the next slide? So as a company, safety is one of our major operating principles, and it's part of our culture that we always start all our meetings with a safety moment. And this is how we thought that we want to start this webinar as well, by giving you a quick safety moment to address the COVID-19 pandemic and how we as a company are addressing it to ensure the safety and well-being of our employees customers, and stakeholders that we work with. Now, the below list actually includes some of the steps that we're implementing on our job sites. And some of these steps include basically include keeping good hygiene and good social distancing protocols, just to ensure that we're limiting the interactions between our people and the clients. And that's just from a safety standard, just for us to make sure that everyone is on the job site is safe. Jay, can you go to the next slide, please? Now, today's speaker, we have Jay Thomas, who is the Vice President of Strengthening at Structural Technologies. Jay has 34 years of experience, of construction experience in the repair and strengthening of commercial and industrial structures. He has been involved in over 1,000 concrete strengthening and repair projects. Jay is a graduate engineer of the University of Pennsylvania and presents this topic for continuing education programs for many national general contracting firms and at the World of Concrete Convention in Las Vegas. His engineering and construction background combined with demonstration tools offer the ability to communicate technical issues that directly relate to contractors. Jay, you can start. Jay, you gotta unmute yourself, please.
There we go.
Yeah.
Good afternoon, everyone. And thank you for joining us. We are grateful for your time. We're grateful that we are all in good health. And I'm grateful for the opportunity here to get dressed up and put a tie and a nice shirt on. I haven't been able to do that too often in the last 40 days. So let's get started. Today's conversation is the adds on to some of the seminars you may have already attended in the last couple of weeks, which is strengthening existing structures. Today, what we're going to talk about are the types of techniques that we would categorize as conventional techniques versus FRP, where we're dealing with either using steel or steel and concrete. Specifically, we're going to talk about using supplemental steel to strengthen structures or steel plate bonding, concrete section enlargement, external post-tensioning, concrete enlargement with post-tensioning in it, and then hybrid solutions. Some solutions I'll show you with combine these different techniques. I'll try to go through the features and benefits of each, some of the limitations that they create in constructability, and also talk about the percent increase that you can get out of these things in each area. We'll talk about design considerations and detailing, fire considerations, and I'm going to go through some case studies, so we're not just talking about theoretical stuff of the use of these techniques. I'm also going to start with, there is a unique difference between new construction type projects and projects that are strengthening type projects, and I'm going to actually start with that today. In general, if you look at what Dr. Tarek talked about in the first two seminars, was the FRP composite. If I take a look at what percent of the projects that happen in upgrading existing concrete structures between conventional and FRP, it's interesting. And I've done this for quite a few years. We do a couple hundred projects a year, and if I take an average of that, it's almost 50-50 every year of what type of what type of techniques get used in these projects. So the point I bring of that is that FRP composites is very attractive, and they do a lot of interesting things. You've heard about their limitations, but to really have a complete toolbox in the strengthening world, you really need to access all these to deal with them. So if we look at the new construction process, and we have basically an architect and an owner working on the function and the look of a building, and a structural engineer coming in to make sure that the load demands on that structure for that use are proper. And you put on a scale, the architectural side, the engineering side, the economic side with the owner versus construction. In new construction, it's very heavily weighed because it's kind of greenfield type scenario versus construction. Now, when you look at strengthening, on the surface, it's a pretty simple scenario. I have a beam or a slab, and it has an existing capacity, and for some reason, there's a requirement for new demand. Or it could be every beam or slab in a structure, or it could be some unique areas. And we're looking for a nice, clean strengthening process to gap that delta between the existing capacity and new demand. I can tell you from being involved in a lot of type projects like this that process is very iterative, not a very straight line. And what makes it iterative is two issues, and they fall in the engineering and the construction side of this process. So, for example, in the engineering side, as an engineer, you may not know or trust what the existing as-built condition is, and you may have to do some type of testing to verify that, to even find out what the actual existing capacity is. We're going to talk today a lot about global effects of repair or of new loads. I put a load on a structure. I have to follow the load path around. I have to see what other issues the repair I'm going to do could do to the structure. We have dimensional and access limits. The building is built. Sometimes there's equipment in it. We have height dimension limits. We have egress dimension limits we have to deal with if it's a retrofit type project. If a structure is damaged, I'll show you a couple of projects where the structure actually got overloaded. What percent loss? What's the residual capacity or existing capacity after that? In some cases, there are deficiencies that we can get as engineers some comfort in living with certain deficiencies in certain scenarios. And there's existing stress conditions in the structure. The structure is loaded, so there's the engineering type stress in the structure that we have to count for in analysis. And also, if we're, for example, building a structure and some type of low strength concrete or some other type of structural defect happens, there's the human stress of having to fix that during the same critical path time frame of the work. So I mentioned it's a little bit more complex analysis, and also the specifications are quite different, mainly because the means and methods and materials I'm going to talk about today are not your typical new construction materials, which means the quality assurance is different. The procurement methods are sometimes different. And in all cases, we're going to talk about these things is creating composite behavior between my strengthening material and the existing parent concrete. So as an example of a global effect, we put a load, say here, a new load on a slab or a beam. And in that process, we have to follow the load path. We have to see how that load affects the slab itself, maybe the connection to the beam, connection to the column. Are we putting enough load on the structure that we have to be concerned about the vertical elements in that load? And then eventually we have to look all the way down to the footings to see what that effect is. Or if I do a strengthening technique using the magic of WL squared over 24, and I cut a span in half, I quarter the demand in these two short spans. However, in that process, the global effect, though, may be that on that slab or beam, I may have shear or punching shear issue I created by putting a support to where there never was one, or I may create a negative moment that I have to check because this slab was not intended to actually load that way in its original construction. From a dimensional point of view, what you're looking at, I'm going to show you this project during the seminar today, is this is a wide, shallow beam that's on a cast below podium slab between these two columns because there's a transfer column hitting on the podium slab right in the center of the span of these two columns. And there's an error. There was an error created that had to be strengthened. Now, as an engineer, you don't have the luxury of picking a depth to make that work. Your depth in this case, because this is a parking garage, is limited to the headroom defined by parking. So in this case, to make it thinner, you'll notice that the use of post-tensioning was used. Some dimensional problems we have on repairs are trying to create more headroom. This is kind of a dimensional issue, but what's interesting here is this is a brand new parking garage at an airport. You're driving into the garage, and it's the first beam you drive under when you drive the helix to get up in the garage, and it's 1,200 millimeters deep. However, a drafting error of cutting and pasting a 1200 millimeter beam was put in. It was supposed to be 600 millimeters. So if you notice how short the shores are here, you'll see that thing is only about 4 or 5 feet high clearance. What do we do with it? We'll talk about it in a bit. We also have issues in retrofit of dimensional limits, in this case related to egress. These two columns are going to be a promenade from people going from a new structure to an old structure, and these columns needed to be strengthened. Originally, an enlargement was to be done, but an enlargement as little as 100 millimeters around those two columns plus finishes created a problem where this egress would not be met. So, and what's nice though, like you talked about before, we have now these new composite materials that are very thin that are fractions of that 100 millimeters to do the same job. There's also limits to access, and our first access I'm going to talk about is access to the structure. This structure is a city block big. It's about 5 stories high, and every column in the building had a punching shear deficiency. So over 400 columns had to have some type of upgrade to fix the punching shear, and what was going to be put in was some new shear drop panels. Now, in many cases, you have access very clear to 4 sides of the column at the slab intersection, but in a lot of cases, there's MEP in the way that you can't shut down. It runs the building. It'd be very expensive, and you have to figure out how to do things on 3-sided. Or column enlargement could be the same thing. You may not be able to get to all 4 sides of a column, yet you have to create some type of strengthening, maybe on 2 or 3 or 1 side. Other access is access of people to the work or the building operations or the structural operations during repair. This is an office building, and this slab above has to be strengthened through the entire building. So the work happens over the weekends, and this area has to be totally protected and scaffolding system put in so people can get above that drop ceiling and install carbon fiber above that to strengthen the slab. To give you an idea of the tight conditions, you can see our worker here, how tight that work is. Now also discussed a little bit yesterday with Clyde's presentation, if you were on it, about post-tensioning, is many cases some of the especially if a beam's been damaged, the shoring has to stay in place during the repair. So I'll show you this project a little bit later, but a 3-sided jacket, basically a 3-sided enlargement, very heavily reinforced, has to be applied to this beam because it's damaged, but the shoring has to stay in place. We'll talk about how some of those things changed. You would never see that in a new construction scenario. So if we look at strengthening, the strengthening process, if we look at that scale, it actually flips over to the heavier to this side in a strengthening application, in that we have to find a technique, a strengthening process that is constructible in the time and space available, that's aesthetically appropriate, that doesn't create any dimensional limits, and it has to cost less than just replacing the element. So what happens a lot in strengthening is you start with, if these are your main criteria, you almost start with means and methods and dollars, and you then see what you can build for a certain amount of money, or et cetera, and you almost reverse engineer into that process. And one of the interesting things about the dollars to replace is we've done a lot of projects that the dollars to repair were actually more than the dollars to replace, but the time frame is what drove it, which, because of liquidated damages or lost profits or some other type of dollar part of the equation, the faster the better. There's even been projects, I'm going to show you one today, that in a kind of a cooperative type of design on a very critical repair, the actual dollar or a financial amount was put out that said, if we can't fix this for X amount of dollars, we're going to tear it down. And we literally start with a spreadsheet that says, what can we do for that amount of money? And we see if we can make engineering sense out of it. All right, so I'm going to start with some of the simple things that relate to steel, specifically supplemental steel supports and plate bonding. If you have room and space to get beams in, like this one, this concrete beam above is being strengthened, and we've got a new beam with some short stub columns going right into the existing foundation. Great way to do that. One of the challenges is probably the biggest challenge is access. Or if I can't drop a column here, how do I connect it properly to the existing structure and anchor it, given all the constraints of the existing internal rebar? The other thing that sometimes comes to challenge is headroom. For example, if this is just supporting that beam and it's not composite with it, sometimes that can end up being a pretty deep beam and create some headroom issues. Another type of supplemental support we've seen is not cutting something or not supporting something directly under the beam, or as I showed before, putting something in the middle, is just taking advantage of the existing conditions. For example, this is a food manufacturing facility. There's a small crawl space below the production floor. They're adding a new load to it, and the plan was to put a steel beam down the middle here and put a new foundation in. And in the process of looking at existing conditions, it found out the foundation, which you can see here, actually sticks out about 600 millimeters on both sides. And the concept was, what if we just post it up right off of that thing at the edge and only close that span basically 1,200 millimeters, and when it ran numbers, that actually created enough of a span shortening to allow that load and saved all the trouble of the new foundation and all the other pieces that go with that. Other type of steel reinforcement could be external bars. They would be threaded high tension bars that would be external to this beam with some plates, and we can actually tension them, and they'd be buried in the top of the slab. Or there's times where if the element is deep enough, where we take drills like you see this drill here, and we're going to drill and either put reinforcing dowels in there, or we're going to put, as I mentioned before, a high tension threaded bar that we can actually tension. The variable is the development length of this. Do I have enough length to develop a straight bar here, or what do I have up above? In some cases, we may use high tension bars that have T-heads in them that basically anchor that. And then there's steel plate bonding, which is really kind of the original carbon fiber system, where we're attaching and making composite a tensile element on the bottom of an existing slab or beam, so that as that element rotates, it engages it. However, it's a little more complex than FRP for a couple of reasons. One, it's not non-corrosive, so we have long-term maintenance issue, and two is I need to both bolt and glue that steel plate up there, basically so that the element goes into tension, it'll engage. And the reason I bolt and glue is, if I look at the sequence of how this is typically done, is you'll typically see mechanical anchors used instead of epoxy adhesive anchors, and then the plates drawn up with these bolts, you stop it at a certain height, and you either inject or somehow get the epoxy adhesive back there. And the concept is, because of the hole tolerances, I can't just attach this to the bolts. I need strain compatibility across that whole plate to make it function. However, from a fire point of view, that creates the same issue that Dr. Tarek talked about with FRP. In a fire, I can fireproof that steel, but that fireproofing is not going to create the scenario that keeps this epoxy adhesive in play. So the concept is, I glue it together so I have strain compatibility during service loads, and in a fire, that glue will probably go away, but I have these mechanical anchors to basically hold that in place as it tries to deflect and keeps it up there. Because of all the drilling and issues we're going to talk about in a minute about not damaging rebar, this is probably one of the more expensive ways to do do a upgrade on, say, on a slab or beam, but unlike the FRP, there's no peeling because of the type of attachment mechanism. Now, this is a project. This is in downtown New Orleans, and this building is being readapted from an old office building to a hotel. And in the process, the center core of this building, which is the lateral system, which is also the elevator shafts, in order to accommodate a hotel versus an office, they had to cut many, many new holes in the elevator shaft to access different floors and make it functional. And in doing that, they put enough holes in it that they reduced the capacity of the lateral system. And the strengthening technique was actually done inside by dropping large steel plates on the walls and bolting and gluing them to the structure. So here you see they're lowering this plate, and they have to be, they could only be so thin to make the elevator system still, the car still be able to work. Now, the tricky part of any kind of plate bonding is this: it's the bolt spacing that's required in design on the plate versus the existing rebar spacing. So here you see a nice, easy, we've GPR'd this surface, we've located the rebar, and we've drilled holes. Now, the sequence to do that is you basically have to literally find your hole and then make a template. Some people use wood, some people use thin plexiglass. We use plexiglass. We lay it up there and we mark the centers of those holes. That becomes the template of the plate that specifically goes in there. Because if I go 2 or 3 floors above this, that hole spacing is going to be completely different because the tolerances and some of the construction issues, you know, how the rebar was put in. All right, so part 2 is going to talk about section enlargement with additional reinforcing concrete, reinforcement and a concrete section. The advantages to this type of system is it's known materials. It's concrete design, which is we know very well. We can easily determine the fire rating because it's concrete and steel, and because it doesn't peel, and because we can make sections deeper, we can have considerable increases in capacity. Some of the considerations, though, are the effect of the repair is we may have to look at the effect of the additional dead load. However, if, say, for example, in a bonded overlay, if that bonded overlay is bonded, that section depth will actually offset that dead load plus add some live load capacity. We have to be cognizant of loss of headroom or other dimensional issues. I can't add 8 inches to a shear wall in a hallway that fouls up the egress, as I mentioned before. We're pumping into some pretty tight voids with a lot of steel, so we need very flowable material. We have to be super careful that we don't damage the existing steel while drilling dowels. And the last part, which is really the biggest challenge of concrete enlargement, is we must achieve composite behavior with the new material and the old concrete. So how that's done is there's 3 key components to that. One is I'm going to be able to create some horizontal shear transfer, A, through the installation of the dowels we put in, and 2, we are going to profile that surface to about 4 to 6 millimeter CSP6, concrete surface prep 6. I'll define that in a second here before we start. So we're going to get some horizontal shear transfer out of that. We're also going to take advantage that concrete, not just the profile is going to help, but concrete's a big hard sponge. And if I can open the pores of those concrete and get my concrete material in those pores, I'm going to create composite action. If during the FRP, if you were on the FRP sessions, you'd note that we did the same thing for FRP. We opened the pores of the concrete, and we're gonna roll on almost a water viscosity level primer that goes right in there. The tricky part with concrete is a much more viscous material, and when I place that material in the form, it will not go into those pores. So I have to create some type of force, some intimate contact between those 2 materials to force it into the pores. So if I go through the steps, step one would be, we're going to locate the steel, and we're going to start drilling our holes. One question is, what type of drill are you using? Typically, you'll see more rotohammer type drills instead of cores, so that if we hit a bar, a core drill will go right through a piece of rebar or a tendon. A rotohammer may not. Then there's the issue of hole cleaning. We've found that through some failures of dowels and anchors, that not cleaning a hole in a dowel literally could half your pull-out strength. So we're either doing wire brushing and air, or a combination of those two after we drill. The next thing is, I have to get to that 6 millimeter profile. And I have a few different options I'm going to show you. One is we can chip. Two is we can hydroblast, which is using 20,000 PSI type water pressure that explodes the surface. And the other is a sponge blast, which I'll describe to you. You may not have heard of that before. Now, if we choose to drill and roughen that surface, one thing we have to be cognizant of: when I'm chipping that surface, I'm creating dust, and what's happening with the drill bit is I am forcing dust into the pores of those concrete, so that the pores that I want to get my material into are now impacted with all dust. So after we chip, we have to either abrasive blast or pressure wash with something minimum, say 350 bar or about 5,000 PSI to open up those pores. Now, how do I do QC when I'm specifying this type of repair? The International Concrete Institute has created some really nice tools. There are 10 of these chips that go from CSP1 to CSP10, and they show you actually what a CSP6 surface looks like, and the guideline tells you how you get there. So as the contractor, you have a tool that you can show your workers of, I need you to get this rough, and as an engineer and inspector, you have a tool to verify that. Now, the other surfaces are, CSP6 is about the middle. Some of them are very almost acid etch and other things, and some are super aggressive at a 10. Now, a couple key things about chipping concrete. Whether you're chipping concrete for a concrete repair or chipping it for this profiling, you should never use more than a 15 kilogram chipping gun to do that. That's about 15-pound chipping gun. And the reason is that when you do that, you will bruise the surface. You will microfracture it. So you'll have a perfect profile with microfracture underneath. Now, a lot of times people would like to use on the end of their bit a bush hammer. That's maybe a say 35 by 35 millimeter bit that has teeth on it, and it looks like it's going to make a profile. Those also should never be bruised, because they've been shown to really micro damage the surface below the area. Now, I'm going to show you a core here. Actually, there's a guy chipping. And these days, we have these pieces of equipment that actually take the load off that gun, so he's not holding it over his head all day. But microfracturing the concrete is the phenomenon you see here in this core. This was a core taken through a bonded overlay that was put down on a structure to strengthen it. And if you notice the repair material on the top, here's the bond line. Looks like it's bonded very well, but look what's below the bond line. It's microfractured. In going back and doing some forensic, it turned out that the contractor used larger than a 7 kilogram. Actually, they used a let's see, 10, it was 70, almost an 80. About an 80 kilogram one, and they fractured the surface. Other methods are this 20,000 PSI hydro demolition done in one pass. It's not that high a water control process. If you can use water, it's very good. And you'll notice to do it, 20,000 PSI creates some interesting PPE requirements for the user, because that actually could cut you in half. Now, ordinary sandblasting doesn't really offer much help for this CSP6. One, it creates a lot of dust normally, and it's hard to get a really rough surface. It tends to smooth it more. There's this technique called sponge blasting where this guy's actually blasting, and you notice there's a whole lot less dust. And the concept is, instead of using typical blast medium that you would blast concrete or steel with, that blast medium is encased in a small synthetic sponge. That sponge is probably maybe 6 or 8 millimeters in diameter, and the medium is inside it. And how it works is, in regular abrasive blasting, the medium is shot at the surface, and the energy creates that abrasion, but it also disintegrates the concrete and makes dust, and it also disintegrates the medium and makes dust. With the sponge, it hits with the same energy, so it does the same abrasion, but it doesn't create dust, and the sponge actually absorbs some of the dust of the concrete. So I'm going to show you a quick video here, and this video is a sponge blasting process that's going to get used for a drop panel, which we'll talk about in a minute, enlargement, that we're looking for that CSP6 surface. And it's being done in one pass. So that is actually sandblasting with sponge, hence sponge blast. Also notice how after you blast concrete, the cracks come out. All right. Other things that are going on in the industry from a PPE point of view are, we're concerned about silicosis. We find the dust from concrete, the silicate in there, is actually as dangerous as asbestos. So some of the drilling also creates a lot of dust, and some of the drilling companies have come up with some very unique ways to limit employees' exposure to that dust. For example, the shroud that goes on top of the drill, overhead or sideways, as you drill, catch that dust, can be disposed of much easier. Or the drill bits that are used actually have a hollow core. And during the drilling, this unit is a vacuum, so it's actually drawing a vacuum back through the center of that drill bit as you drill. And it's collected right within the drill. Notice the difference. Overhead. All right, so we've let's say we're forming pumping the bottom of this beam, a drop panel, a bottom of a slab, whatever we're doing here, and we've roughened the surface to CSP6. We've installed our dowels and our reinforcing steel. We've got our formwork up and the shoring to hold it up in place, and we've got a gate valve that we are going to pump the material into that form. And we vented it in a couple different ways. One is to make sure that I'm getting material to a spot and that I'm getting up to the top, is we'll take PVC pipes and drill a hole in the form and put them in there. And notice this is cut at a 45-degree angle. The concept is, as material flows in here, it will be able to get in the pipe, come out that pipe, and we'll know where we have material. We'll know what we've gotten at the right place. So I start pumping and I fill the form. I've got materials coming out my pipe vents and my form vents, which I'll show you in a minute, and it's filled, and we're sure it's filled with good material, and we don't stop there. So the only difference between this and regular pumping of concrete is the next step, which is, instead of stopping, I take the pump and I give it a couple more strokes, and I'm basically creating pressure inside that form. And the concept of the pressure, and that pressure is measured in one of two ways. I either measure on the back behind the gauge a back pressure in the valve, which is somewhere between 6 or 8 psi or 0.5 to 1 bar, or I have on my formwork, I have formwork gauges that measure both the head pressure, and then I can see the additional pressure on. But the concept is, I need to push that material. I need to take that material and force it into the pores of that concrete, especially in this orientation of shape where that material can't be pushed up into the pores without pressure. And then I get my bond, and I ensure I don't have a cold joint. Then I close the valves. It'll hold that pressure for about 5 hours till it sets. All right, so here's an example of a form and pump project. I have a beam. It's got some flexural cracks in it, and I'm going to basically create a 3-sided concrete jacket around the structure to increase its. Turns out it was deficient in shear and flexure. So I've got everything in place. I've roughened the surface. I've opened the pores, and now I have to put formwork in place to do this pressurized form and pump material. So if you look at the formwork, it's not that much different than any other formwork you'd see, with the exception of there are vents that we cut at the top sill. Let me get my laser up, please. At the top sill here, every so many, a certain distance, how far we're pumping, we'll cut a wide vent in there so material can get out of it. We also just attach these whalers to the side of the form so that at 1 to 2 psi, I don't blow the formwork out. So the process is I'm going to pump into that gate valve until the material's filled. When I have solid material, not just fines coming out of all these vents, I then take a wedge and I seal that. And now I've got a closed form that's filled, and I do one more thing. I just pump it a couple more times. I create that back pressure in there that I either read a gauge behind the valve or a gauge that's on the form. And that creates my 1 to 2 psi bond mechanism. I close the gate valve. All right. This is the form. This is a form pressurized mechanism that's literally on the form, and it's a spring-loaded plunger, and it's calibrated out. So I'll show you a video here. What you're looking at is this gauge has been placed on the bottom of a drop panel that's getting pumped. We've filled it, we've capped it, and we're now going to pressurize it. So what you see here reading is the pressure head of the material that's in there, which is SCC, which we'll talk about in a minute. So we've got a liquid head, and they're going to pump. They're going to give it one more pump, and there's your 1 psi pressurized. Very simple. And then here's your final beam. And of course, in retrofit, in many cases, we can't move the MEP or certain things out of the way because the building's functioning, and things like sewage and waste and other type of water or electric have to continue. We have to work around them. Typically, we use SCC for this type of repair because of its flowability and ability to consolidate and not have to vibrate, and almost guarantee no voids because of the flowability and the rheology of these materials. To give you a perspective, I know that in the region there, SCC is used quite a bit, but just to give you, this is a form with a plexiglass surface on it. To give you an idea how flowable that is, when it goes into the structure, you'll see this is just getting poured in there, and you'll understand why you don't have to vibrate it. It literally flows like water and pumps very well. Okay, here's an example of a adaptive reuse where this structure has actually been torn down to core and shell. They're putting a new facade on it, and on the roof they're going to create some areas where people can gather, and also a green roof, which is going to add load to the structure that has to be accommodated. And what I want to use this example for is related to different techniques that are used in the strengthening world for either shear drop heads or large drop capitals. So from a prep point of view, what we're going to do is we've got a roughened surface. We also typically saw cut around and chip back to the cover so that we actually tie into the column. and then we form it up. And the size of this panel really can do a couple different things. So for that specific project I just showed you, you've got what was shown in analysis under the new loads was you had negative moment deficiency, positive moment deficiency between the columns, and also punching shear issue. Now, if I do a small drop panel like you see over here, like a shear head, something between, say, 300 and 400 millimeters, I get it in there and I make composite. I've increased my structural depth because my slab, top of the highest bar is deeper, so I can take care of the punching shear. Now, for the positive negative moment, I could use FRP. So I put FRP on top. If, however, I take that panel, instead of being 300 millimeters, I take it out to L/6, the span over 6 in all directions. And what that does for me is, now as a drop capital, that increases my negative bending capacity. It still increases my structural depth for punching shear, and in all likelihood, it has reduced or eliminated the positive moment demand by putting this capital in. And from a cost point of view, from the smaller one to the bigger one is minimal change. Sometimes we do this on slabs because we can't get to the top surface, or the top surface has some issue on just related to some other type of access. And again, the key to this, especially an overhead drop panel, is I can't just pump that material into that form. I need to pressurize it to drive the concrete into those pores. So, for example, sometimes you've been asked, wouldn't it be easier to core a hole and just pour that SCC material in there? And the answer is yes. With SCC, I will fill that form, but there's nothing's going to push it up into those pores. I could pressurize it from up here, but now I'm taking a chance with all this drilling around the column with all the steel or PT that's there, and sealing a hole to pressurize it in concrete versus in a form is much more difficult. And if I don't get a bond, my structural depth hasn't changed, that this is composite, so I haven't affected the punching shear. So in application, what would cause, other than added load, what else do we see happening that requires drop panels? One is some such scenario where the top steel is too deep. It's placed too low. Either steel's too low or the PT tendons are too low, and my punching shear depth has dropped. Now, that could be fixed with a drop panel. Now, here's a garage. This structure, as you can see, collapsed. But notice it's nowhere near carrying its maximum live load. And in analysis, when they analyzed this, there was two things going on. One was the top bars over these columns were too low. So the punching shear capacity was deficient from day one. And two was they let this structure, they didn't pay attention to the durability side of the structure. And as those bars started to corrode and get consumed, they became smaller and smaller until it actually failed under partial live load and dead load. Here's the beam I showed you earlier in the presentation that was too deep. And the repair was to take 750 millimeters out instead of the 600 that was needed, and form and pump back 150 millimeters. And in opening up this area here, that gives us room to figure out how to couple to the existing stirrups and make a closed loop, add the original steel in there, and then place this concrete. Now, if you look at this concrete, here, you could actually access the side of this form with a bird's mouth. But again, much like a drop panel, if I pour the material into this form through the top here, I still have no intimate force to push it up into the pores. Whereas if I form it and pump it and just give it that last pressure shot, I ensure composite action. Here's a column. Yes.
There's one quick question that rose up. I mean, you talked about in the previous slide, you talked about solutions for punching shear using drop panels.
Yes.
The question asks whether can you actually solve punching shear issues with a bonded overlay instead of only like a drop panel or a shear cap kind of thing?
Absolutely. We're going to talk about when we get to drop panels, because if I put a bonded overlay in, think about it, my structural depth increased because the bottom of my slab to the top of the highest bar got higher? Great question.
All right.
Now in columns, this happens to be in a refinery in a seismic zone. So as you can see, the typical seismic, really tight tie spacing. Most of the time when we pump columns in this, you're not going to be able to tremie this down with a hose because you can't get a hose down there, and you've got a structure on top. It's not an open form. So we'll typically pump these from the bottom up. We've gone as high as 10 meters. Here you see the column here when it's finished. Another tricky thing is there is, even in new structures, I say new, it could be under construction, it could be a couple, 2-3 years old, the desire to remove slabs to create atriums or higher height, things like that. And in the process, the issue is we unbuckle a column, and the buckling load to buckle that thing quarters. So and our reinforcing steel has to be continuous through the slab. So you'll notice here, here's a bar coming up. There's a bar coupler, and there's a bar going through the slab. So the process to do that is a little tricky, because you can't take the slab out because you'll unbuckle the column, and you can't, and the slab's in the way. So we're going to take advantage of that piece of slab. And the first step is we're going to core holes. We're going to core holes around, like you saw in this previous slide here. We're going to core holes through the slab where we're clear of the steel. We're going to drop bars through there and grout them in. Now we have a bar we can couple to. We're then going to, on the bottom slab, we're going to put new steel around it, and we're going to form and pump it right up to the top here. And then we're going to go up, and we're going to repeat that up above. Now we have a column that is actually strengthened, and you can demo the slab. So typically you'll see like rough demo up close to the slab, and then kind of dental work demo really tight. And the original slab becomes part of that column, part of that strengthening. So this is one that was actually done at Dubai Mall. Let me go to the next slide, show you what's going on. There was a slab in here. They wanted to use this area as retail and other things. They want to open it up. So the columns were strengthened. The columns were here you can see here the column. This one's going to get poured up to the bottom of that beam, and then the top's going to get poured. And here you see where it's filled in, where they kind of cleaned up that slab, so it's nice and pretty, like elliptical column here. And they just put this formwork up and form it around there, make it nice and clean. If the only other technique you can really do that by taking the slab out is you have to brace that column 4 ways with tube steel like this. This was actually a punching shear failure from overloading the slab around this column, and the whole slab had to be cut out and put back. And they decided to, since it was just one location, to basically brace it, take the slab out, put the steel in, put it back. Another thing we see today with the speed of construction is either a reshoring sequence that's going too fast, and that could be on slabs, or the shoring sequence on pour strips where they're pulled too fast and you get some deflection between them. Or once this reshoring jumps up one more floor, this slab, while it's still technically green, is getting loaded up with heavy tiles, windows, all kinds of construction equipment and debris. And the effect of that is basically a deflection in the slab, and that where it deflects permanently. It's okay capacity-wise because the right steel's in there, and sometimes they'll even you'll see cracks near the columns like this all the way through. Now, typically when that happens, that could be, I've seen as much as 80 to 100 millimeters of deflection in this process, which creates a serviceability issue if you've got a condominium or cabinets or doors or walls. And the typical thing that the contractor wants to do is call the floor leveling guy and level this out. And the added dead load of that can really be a problematic. If you add 1 inch 25 millimeters of this material, you are taking 60 kilograms per meter squared away from your live load. So there's scenarios where if you have an average of 150 to 100 millimeters, you can half the live load in certain structures. And but the concept to make that work would be don't have your slab with this dead load on top. If you make them composite, what the question asked before with the overlay, you've made an overlay, and you've actually strengthened the structure. So for example, the punching shear question before was, if I bond this overlay, it has to be bonded, and I put steel in it, which requires, my experience is you need at least 100 millimeters to get some type of thin road mesh or small bar in. But I've increased the punching shear depth. I've increased the negative moment because I have additional steel up here, and I've increased the positive moment or because my D is now deeper for this bar, all by putting on that amount of weight, but bonding it. So here's an example. This is notice this area here. This was early formwork was removed. They had huge deflections in here. They also found some negative bending issues. So you can see there's some negative bending steel put in, plus all the steel. And at 50 to 100, or even say 50 to 100 millimeters, when you pour that material on that concrete, the head pressure of that material is not enough force to push it in the pores. But what's nice about an overlay is if you vibrate it, you get liquefaction of that material, and it'll drive it right into pores. So in a case like this, in a big area, you would basically use you would use a vibrating form to do that versus pencil vibrators. So here's another video I'm going to show you, and this video is when you pour regular concrete into a overlay like that. You think of it being liquid, but if you looked on the bottom and saw what that surface was like, you'd be surprised, which is what you're able to do here. I have a piece of plexiglass. Think of this as the bottom of the form, and look what happens when it goes in just under its own head versus vibrating it. So imagine that's the bottom of that's your bottom surface on that overlay, that you're trying to get that type of concrete in there, but now you start vibrating it, and you get that liquefaction, and it goes right in the pores of the concrete. Perfect bond. Now, in all cases here, with all this enlargement, the key point is, how do you quality control that you do have composite action? It's pretty easy. You can hammer sound it, you'll hear hollow spots, but the true test is, let's do a core. Let's core, and the size of the core, the diameter of the core is related to how deep you got to go. So you could be anywhere from 50 millimeters to 100 millimeter diameter core you may have to make to do a pull. But the idea is you core at least 25 millimeters into the parent concrete. You glue this round steel dolly on there. It's got a female thread on it, and you put a testing piece of equipment on. You pull it, and you're looking for certain criteria. This is both American Concrete Institute and International Concrete Institute guidelines that say anything over 150 is good bond of concrete to concrete. Up 200 above is excellent. So I have a question for you. Yes,
Jay. Before you ask your question, one of the questions that appeared based on the bond is, what is your take on using bonding agents after you surface prep the area? They haven't seen that in your slides, so if you can shed some light on that.
Okay, so I'll give you my opinion at the end, but I'll give you the two sides to this. So one side says, okay, you still have to open the pores of the concrete, because your bonding agent is not going to bond to concrete unless it goes in there. So you don't save any preparation. So the question is, do I want a bonding agent in these concrete pores and assume that my concrete up here is going to basically adhere to that, or do I want my concrete in there? And a lot of tests have been done that show if some bonding agents, if you do them right, they work, they may get you a good bond. Others show that especially in form type work or work like this, where when do you put the bonding agent on with all this steel here? Does the bonding agent get on the steel? Is that an issue? But you're adding a cost that looks like it doesn't add anything. And if you want to go through to keep it simple, let's get our material in there in those pores. It's only a vibration process. So I will tell you, I have not been on a project where we have used a bonding agent in probably 20 plus years. Because most of the industry says, let's get the material in the pores, not the bonding agent. There's also scenarios with bonding agents, like if I'm forming a repair, that there's a window that I cannot meet of getting the concrete to that by the time I let my form work up and get going. So it's an added cost. It's equal or worse at best, is what we found. All right, now here's the proof of the pudding of all this sort of stuff. Whatever you're going to do is that bond test is what tells you what it's doing right. In many cases, sometimes we should be doing mock-ups to like do a small panel and do a bond test overhead, do a overlay in a small area, do it overhead or down, and do bond test. So we can show the engineer, the inspector, this is the prep we're doing, this is the installation technique, here's the cure time, I pull it, I'm over 150 PSI. Now there are some limitations to that bond test. As you get too deep, it's very hard to get a core not to break if you're real deep. So what we do is we just do bond tests with our prep on something that's, say, 100 millimeters deep, which is really safe. Anyway, what's in the quality control, if I asked you what you're looking at is a core, this is the top of this is the outside of the slab, this is the parent material, this is the repair. Here's the bond line. I got over 150 PSI bond on this test, and look where my bond failure is. It's in the original concrete. So if I asked you, where do you think the best location is that should fail and why? And most people say, I want it to fail in the parent concrete, which is failure number 4. But I want you to think about this. The places I've seen it fail are in the parent concrete, at the bond line, in the repair material, in the repair material deep, in the repair material not so deep, and sometimes the dolly even breaks off while the pod. But if I said to you, I have all of these cases happen, but every one broke at 150. If these 3 break at 150 and number 4 breaks at 150, what does it tell me about the bond line? It tells me the bond line is actually more than 150. So the location of the break is not as critical as you think. It's the break strength, and where it broke. If it didn't break at the bond line or anywhere, if it didn't break at the bond line, that means the bond line's higher than that break. All right, so while we're talking about form and pump, this is just a use of form and pump you'll see out there, which is fixing honeycombs or voids. Honeycombs meaning, like you see here, where you have rock pockets because you've had segregation during placement, and void here where it appears that they just didn't vibrate it and get it in this corner or something along those lines. Now, what reality is if you have these type of scenarios, like this one here, the engineer wanted to look into this a little more, and they asked, we were on site doing a repair, and they said, could you just take a look at this? And when we hammer sounded that, it didn't sound right. So they took a chipping gun. I'm going to play you a video here. They put this chipping gun, and this is a shear wall. Fortunately, there's no floors above it. That shear wall, the shear wall condition, where are you? Now, this is that wall that just showed that small defect at the edge. And as they get a little closer in the video, you're going to notice there's something missing in that concrete. What's missing is the cement. That's a honeycomb or void. Now, and a very high percentage of the time, what causes that is the concrete's been dropped too far. In this case, that's what happened. They were dropping that concrete from over 3 meters from above, and in that shear wall is a pretty good amount of steel, both across it, both horizontal and vertical, and they're dropping it, and the concrete's hitting that steel, and the cement's going one way, and the aggregates going the other way. So, in the process of placing vertical elements, there should be great care and quality control of how those are done versus trimming. Putting the hose down in there should never really be dropping concrete more than 3 feet into vertical elements like this, or you can get these kind of problems. We also see it prevalent in, and this is a really good application for that SEC, is in these big shear walls where we have very, very tightly congested boundary condition steel here at the edge, which is where you see these honeycombs. As that material's dropping down there, it's just segregating, and you have almost no strength to it. Another thing we see that sometimes they go form and pump is steel placed too close. Too many lap splices next to each other. Steel placed too close because they can't fit it in the form. And you know, the interesting thing is, if I go out to a construction site and I ask a seasoned construction worker or inspector to ask them what's the maximum spacing between minimum space between bars, they won't know it's 1.5 times the aggregate, because it's the aggregate that you can't get through there. Now, we say to them, do you have a check-off process, pre-pour? And they say, oh, yes. I said, but you poured this. You could, and you can see the concrete. It's not, even SCC is not getting through there. Yet these things happen and get poured, and they're very, very difficult to fix. One of the challenges with fixing a void or repair is they look like this on the surface. If you chip them out to where they're bad, you get this odd geometrical shape that's going to create a problem with all these reentrant corners and cracking. And most repair and removal specs, ACI and International Concrete, may say you should make this somehow rectilinear in chipping. Which this is a shear wall in a seismic zone, quite a bit of steel there, and one pour they had. So imagine it's not going to be easy to make this thing rectilinear, and people try to cut corners and fill this up. It's also not going to be easy to form this and get material flowing into it because it's closed, which is where the form and pump comes in. All right. Part 3, we're going to talk about external post-tensioning. And in external post-tensioning, we're doing one of a couple things here. One is we're taking a post-tension cable and is literally, as the word says, is external. I create a dead end, I create a deviator of some sort, I create a live end, and I tension it, and I create a uplift moment, a secondary uplift moment that either counteracts new loads, or I could do it for serviceability. If I got stiffness issue or deflection issue. Now, just like carbon fiber, which Tarek talked about, is I can leave this exposed if it's supplementary. In other words, if the post tension goes away in a fire and it's supplementary, I may not have to fireproof it. Or if it's for serviceability stuff, I don't have to fireproof because obviously the structure is not going to collapse. If that's not the case, I have to put it in concrete. So I'm basically going to do a jacket, and the PT will be inside of it. Now, this just creates an uplift force. When all this is bonded, not only create an uplift force, but they also, since they're composite, they also they'll be adding pre-compression too, which is so now I can do much higher upgrades and things like that. All right, so considerations are: is it casting concrete external? I can get sizable increases out of these. Am I draping it, or am I deviating 1 or 2 point? The tricky part of this is all the detailing of this anchor, because I need a lot of bursting steel in this area to confine that. And I also have to be careful of I can't have excessive uplift forces because I could create a problem if they're putting a new load on this thing, just like a transfer girder. I may have to phase stress this thing as load goes on it. Here's a slab. In a slab, because you can't deviate it within slab, actually we use king post at quarter points, and this one is actually in a large villa in Dubai, and they had a deflection issue which was solved with these tendons. This is a structure. It's a historic structure in the United States that was designed by a famous architect. It's called Falling Water. It's a home that was built in the 40s that literally sits on top of a waterfall. The waterfall flows through it. And has these two large cantilever balconies, concrete balconies, that were deflecting. They had deflected almost, say, 150 millimeters. You can see the emergency shoring in there. And the repair was to use internal PT on sides of the beams, the cantilever beams, where they're actually deviated up like this. I have a deviator block. I have a dead end there, and I'm going to stress this end. And all they wanted to lift it was 12 millimeters, because the forces to do just 12 millimeters was about 400,000 pounds to do that. So all they wanted to do was make sure they grabbed it. This is a change in use project that's going to use all kinds of different scenarios. So this is a large hardware store, Home Depot over here, maybe like one of your big Ace Hardware stores over there, and it's in a part of the country where there's no area for parking. It's in the Washington, D.C. area. So they build multi-level garages. And when it was built, the supply store was not really servicing contractors. Now these big box hardware stores are their biggest clients or contractors. And unfortunately, this was rated. No trucks could go in there. So these guys are getting no contractor business. So I'm going to show you the strengthening techniques that were on here that show a lot of things I talked about. The global effects of repair on a structure, the financial side of it, working a replace versus fix. So the way the first thing we had to do was the existing capacity of the stem here was determined by engineer record was deficient. And basically we were on a team that they said, what do you think you can do to fix this? And we did an external PT system. Now there are in this project and others, there was one job we did, 1 million square foot garage, 100,000 square meter garage, where we do 9,000 of these stems. And when we did that garage, we had to come up with a way of really becoming efficient. And how do we make this anchor? We can't cast concrete. It's going to be too expensive. So what we did was we came up with a system that we drill a heavy wall pipe through the top here. Our VSL team takes a tendon and actually bends it for us like a hairpin. We have deviator clamps in here, deviator quarter points, and in the center, I'm going to show you the anchor block that they do, that you put in the middle. So I have basically a tendon on both sides of this. All right, so here's the components. Here's my deviator, here's my pin. Notice it's grouted because you have to drill a bigger hole. Here's a global effect on the structure. If I don't grout this and have full contact, the force that's going to go on that pin would split that T right in half. Here's my deviators, and here's my block anchor in the middle. These two tendons come in, and they're dead. They're the dead anchors. These two stick out, and they're the live anchors where we stress. And we've got these long tails on them, so if they ever want to go back and do a lift-off test for stress or re-stress them, we can get at them. Now, what do you think the driver of this system we put in the first time was? What do you think the most expensive part was to do? Because on this project, the owner sat us down with the engineering team and said, if we can't fix our project for $5 million, we will be tearing it down. So as a contractor, I go and an engineering support company, I sit down my contractor, my engineer, and I say, okay, what's the most expensive thing? And the most expensive thing on this deal was drilling that hole, because there were 8,400 holes that had to be drilled. Not at the Home Depot one, but the million square foot garage. And we sat down at a spreadsheet and we worked this up, and the driving force was drilling. So we worked backwards. We said, if we can't drill this hole in 10 minutes, this job's done. They're going to tear it down. So what do you think the first hole we did, how much time it took? And what we did was we went out and purchased this drill. It's very interesting. It's almost like a backhoe arm. It's got a giant drill on here that locks itself in. It drills this hole, spins 180, and drills that hole. And because we had not thought of the type of cores and the amount of water, the speed, the first hole took us 20 minutes. And we said, oh boy. So over the course of engaging drilling experts and coring experts and water experts, we actually got it down to 8 minutes, and the project happened. So that takes care of this double T-stem deficiency, which also, by the way, had a shear deficiency, which we were going to be able to deal with a carbon fiber U-wrap. The next thing was the slabs. Under the new truckload, the bending of the slabs was deficient, both positive bending and negative bending. So to deal with that, and there was a shear issue between the flanges in multiple locations. So to deal with that, we're going to do a bonded overlay like we talked about before. So here we have the surface has been prepped. We've got this road mesh on there, and we're going to pour it on and vibrate that and add an overlay to deal with that. So now the load path, okay, we come to here, we're going to deal with the shear. Also the inverted T's here, they were deficient in bending. And then at many of the connections where that inverted T sat on the haunch, this haunch had a shear problem, not vertical shear here, but actually the T breaking off. And that was remedied with this tube steel haunch addition for support with a bearing underneath it. And then also the flanges up across the top here, when the truck would go off, it would have broken that flange. And then that was remedied with a thick angled plate bolted on, also with a isolation bearing for movement on there. So you can see the kind of the following the load and doing all that. Now this is a beam. This is a 3 meter by almost 20 meter span, 3 meter deep, heavily post-tension beam that was overloaded with something I'm sure you won't see over there when they piled a snowstorm up on top of 2 of these beams. That was over 2 meters deep, and it failed the beam. The beams at about quarter points had this failure. So this has got some interesting points to it. Now I could see this happening over there with soil or construction material or concrete debris, but on this is the first question was, hey, should we remove or replace this? And it's a brand new structure, by the way. It's barely occupied. It's on the surface. It says, hey, let's replace this thing. But the problem with that is that the slab above it is PT, and it's the beam in this column line here. So you take the PT down so we can take those beams out. This whole bay from top to bottom has to be shored up, and that's the turn aisle. So now you can't get into the garage. The other tricky thing I'll talk about was, this is a beam I showed you before, is I can't remove that shoring during placement. And then the third thing was, what is the capacity of this beam? If there's going to be a design, because the design is going to be a 3-sided jacket in concrete, what's going to be the design capacity of that jacket based on this scenario? And so the repair goes like this. First, the cracks were repaired. Then the surface was fixed. The surface was prepared. A PT system is put inside there with steel. And the concept was, this happens a lot in damaged structures, is let's assume this section has 0 capacity. We know it doesn't because it didn't collapse. But let's assume it has 0 capacity, and how about the design in there carries 100% of the factored loads, which is very simple. It sounds conservative, but the amount of PT and steel goes in there is minimal compared to trying to figure out what existing capacity. One other thing about the global effect, if I'm going to put enough PT in this structure to deal with the 100% of the factored loads, I still have PT forcing these guys, and I may over-compress or over-pre-compress that element, so I have to release them if I'm going to do that. So there you see the formwork. We're going to pump through this port here using SCC. And there's our beam around a beam at half the cost of taking it out because of all the ancillary things and the parking issues. All right, so now let's get to the shoring. I believe if you're on the PT repair and evaluation of what Clyde did yesterday, he showed you a version of this. But what we typically do is either with tube steel or circular steel that I can remove, I'm going to take one of these post shores out at a time. And I'm going to place this between this on the top of the post shore. It's going to bolt to the bottom of the structure. And because it's tube steel, it's easy to form around. And my stirrups can get past it that way, and my bottom steel can get past it this way. So I don't interfere with anything inside. I'm gonna put on my formwork. I'm gonna pump it. Now, when I'm done, I remove my formwork. I have this stub sticking out of there. That in this case, I'm gonna cut it off and grout it. Or in the case of the removable ones, they're circular and they're threaded up in top, such that I can basically pull them out and just fill that grout up. This is the structure I showed you before, where I said you only had so much headroom to fix it. It's a podium slab with a low-rise condominium on there. And this crack here was what was pretty scary. What started that first repair that I showed you earlier, and it's pretty scary because it's a punching shear crack, and you could almost start to see the punching shear. The other part that was scary is this was the column coming down from the pool, which is carrying the load of the pool. So this structure would have absolutely seen 100% of that load. And if you ran the numbers, I'll tell you, this is one of the few structures I've seen that actually would have failed under that load. So here's that repair I showed you. The problem was two things. One, the amount of PT force and pre-compression at slab was a little bit short. And two, the contractor, when they placed the PT, had the drape wrong. It was up too high, which creates less uplift moment. And the combination of those two is why we needed this new piece on the bottom with the PT. Now, after that happened, they brought in a third party to evaluate the rest of the structure. And before they were done, every column line, north, east, west, and north, south in this structure had to be also strengthened. So the first one I'm going to show you is this piece right here, and the second one's going to be looking at this T section as you look here. So to give you an idea how much is going in there, this is before the bottom formwork goes on. Got a lot of PT in there. We have to sleeve all the new mechanicals through there, right? Here's that T section where you've got all this material coming in, and we pumped the full length of this at one time. And here's all your NPT to stress. So to make sure we know where we are, the other thing we'll engage in some of these repairs is we'll put plexiglass windows in the form so we can see what we're doing and where we are. And then here's those pipe vents that I had described. I want to know when I get to this point, I want to know that I'm not trapping any concrete behind this column as the material rolls by it. And you can see them spaced out through the whole repair. And that's the finished product. This is PT that's going to be internal. We're literally going to core through a center of a beam and install a PT in there to clamp it together. The problem was on the structure was the top bars, and there's number 10 bars. The top bars in this thing were not hooked or T-headed, and they were too short. So not developed long enough. So they're right at where the end of the bar was. You'd see cracks. It was basically pulling apart. So the repair is going to be 4 holes through the structure drilled, anchor blocks, and then PT force. Now, on paper, that doesn't look that impressive, but that structure is a 450-foot high preheater in a cement plant, and this is 30 meters from here to here. And this beam is, let's see, 3 meters deep, and this way, this is about 50 feet this direction. So what I just described, what has to happen on 7 levels is coring that length and putting 3 million pounds of pre-stressing force on to hold it together. And the reason they did it, that fix was, the fix to do what I just described was about 75% about 25% faster than tearing it down and putting it up. And at the loss per day, that was a huge amount of money. So they decided to go with the fix, even though it cost more than the replacement. And here's the coring drill. Very interesting coring. Our tolerance to come out the other end was 25 millimeters horizontal and vertical. And it's a very interesting drilling rig. It's probably got about a 5-meter mast on it, so they can actually somewhat have a little bit of control of steering that thing. And it was gauged the whole way through the hole by down the hole and externally with some NDT equipment of where it was going. Let me jump over this one. All right. Oh, no, I got time. All right, this is a classic raker beam, which is a beam you'll see typically in stadiums and indoor arenas. And it's made to hold the precast seating that overhangs typically the suite boxes and the club boxes. And obviously when it gets loaded up, it rotates and you get these tension cracks. You know, these are high tension zones here of cracks. And what happened was, as they were setting the tubs on top, they started to notice every one of these were cracking. So you can see the emergency shoring in there. And there's supposed to be number 10 bars that come out of the slab here and turn down and go across those cracks and develop themselves to stop that from cracking. But what happened was the bars were too short. They were very, very small distance across there. They weren't hooked, they weren't teed. So it's literally pulling out, which is why I create that crack. So there was two different repairs done based on the level of deficiency that was calculated by the engineer. The first one was this first raker was we were going to put carbon fiber around a closed loop around that thing, but to do that we have to cast this concrete wedge to make it so it was square to do that. And here's a picture of it. Here's the wedge dotted in by red. And in some cases we only had 25 millimeters or so to slip the fiber through, which was nothing nice about the fiber. That was easy to get through there. The second raker beam was much more deficient, and the crack is right here, and there's a beam, and then the seating is up top. That required 4 almost 50-inch diameter, 50 millimeter diameter bars that were threaded, and a crosshead to make it square to do that. So we drilled holes down through that 1-meter beam, deep beam. We used T-headed bars so they could be anchored up top and not create any problem with the seating. And then the bottom here, this crosshead was pretty heavy duty. It's a large steel element that's going to get torqued up. And this is fortunately in between the walls, between the suite boxes, so you can't see it. So as a joke that they were serious about, the owner, and when it was all done, on the first event at this stadium, which is a basketball arena, we were told that we were going to be invited for a proof load test, that they were going to sit us, the engineer, the contractor, and us, they were going to sit us on the edge of the second level to make sure it worked as a proof load test. All right. Last thing I want to drop in is kind of relates to strengthening, but it's an interesting numbers game here. Many times on jobs we have low strength concrete, and it can create big problems and slowdowns, and the fix sometimes can be a nightmare. But I wanted to go through what are the effects of low strength concrete on flexural capacity, shear capacity, and axial capacity. And let's get extreme. Let's say we're supposed to have 10,000 psi. Or as my astute converter told me, that it's at 68.947 megapascal, or versus we get cores and tests that say it's 3,000, 20 MPa. Let's start with flexure. So if we look at our flexural design, and one of the key variables is D for the center of our compression block to steel, right? And we know that one thing interesting happens here. When F prime increases, the neutral axis shifts up, correct? So my neutral axis shifts up, therefore my D increases, right? Now, and when it goes down, I have to grab more concrete to make this equilibrium work, right? So I got to grab more concrete. My neutral axis goes up. I don't. So if we go back to the formula, I'm going to take a column here that has these variables. This is the geometry. Here's the area and steel, and I'm going to vary the difference from 10,000 down to 3,000. So at 3,000, with that change of neutral axis, what happens in this scenario is the neutral axis changes from 3 inches to 1 inch, or changes. It comes down 3 inches versus 1 inch. So at 3,000 psi, I'm at 3 inches. At 10,000 psi, I'm at 1 inch, right? So let's look at the moment capacity change. At 3,000 psi, if I run that formula, my moment capacity is 206. At 10,000, it's 216. It's only a 4% increase in that, decrease in that process. So for flexure, it doesn't have that. It's a minimal effect. Now let's look at shear. So for shear, use this beam here. For shear, the F prime C comes into play as a square root, right? So there's my contribution for my concrete, and that's my contribution for my steel. So if I do the same thing I did before at 3,000 psi, and I solve that formula, I'm at 70-some kips. At 10,000, I'm at 100. So my capacity decreased about 30%, which is moderate. That's a reasonable decrease. And there'd be some punching shear effect too, because that also has a VC element, right? Now let's look at axial. Now it's straight up. There's concrete contribution. There's my steel contribution to the axial capacity, and I'm dealing with straight up F prime C in the formula. No square roots, right? When I do that and I take the area of the steel, I change from 10,000 to 3,000. It's basically a direct ratio. At 3,000 psi, I have 1,000. At 10,000 psi, I'm almost 3,000. So it's almost the direct ratio of the loss, which makes sense in that. So with that, it's 1 hour, 29 minutes, and 16 seconds. That's pretty good shot, right, Akram?
Yeah.
My timer going.
Right on time.
Can we have plenty of time to talk questions, though. If there's questions, let's go through them.
Yeah, sure. So again, before we get into the Q&A, first of all, thank you, Jay, and I wanted to thank everybody who joined us today. I'd also like to remind you guys to fill out the short survey if possible. Again, it will only take a couple of minutes. And now we can get to the questions and answers. So, Jay, you have talked about using the form and pump technique. So I wanted one of the questions that asks, first of all, if anybody wants to specify this technique, what are they supposed to do to specify it? Where can they get some more information about it from the codes?
Okay.
And
all right, good. Go ahead. I'm sorry.
No, that's it. Yeah.
Okay, that's it. Okay, so if I summarize what a key specification on form and pump should have, it should have 1, experience. 2, you have to design the form work. You have somebody be able to design the form work. 3, you need a design mix that's pumpable, and 4 is the pressurization. How do you ensure the form is pressurized? You have to have some type of QA/QC to do that, and then some QA/QC after a pull test. Now we have a Word doc of that, many versions of that we could share with you if you're interested. It's not proprietary. It also refers to American Concrete Institute. They call them RAP. They're basically RAP guidelines, RAP, Repair Application Procedures. ACI RAP 5 is what form and pump is based on. So you can get a generic spec, and you can also refer to RAP 5. And we'd be glad to share one with you, cut and paste and use as needed.
Sure. The next question talks about the punching shear. You've also talked about strengthening some existing structures for punching shear issues. Now, if you want to strengthen a slab for punching shear, and you're actually introducing a thickening for the existing or an inverted drop panel, do you actually consider in your calculations the existing punching shear reinforcement?
Yes. Well,
so
well, you know, structural depth is bottom of your new drop panel to the top of the highest bar. So we are considering that, or we're taking that in consideration, and that has some existing punching shear capacity. So we're not, you know, we're just filling that delta. Remember, existing capacity, new demand. So we're taking the existing capacity in consideration, and then the top steel that's in there is critical. It's now part of the new structural depth.
So for the inverted panels application, you've also showed us that we're going to be drilling 2 L bars for as a main reinforcement. And the question says, how can you actually drill 2 L-shaped bars in the column and the slab at the same time?
I'm going to go back to that slide and see if I can understand what the question is. I guess assume the question was related to what they saw on the slide.
Yeah.
Two L-shaped bars. I mean, these are just L-shaped dowels, and
Exactly.
these are just straight bars. Yeah.
So
they're not really they're just dowels, L-shaped dowels, and they end. And you'll notice up here the same thing. They're L-shaped dowels that are dowels, plus they're there for the constructability of the bottom bars you can tie something to.
All right, so basically you have the main reinforcement is going to be straight bars, and then you have your L-shaped dowels that are tied to the main reinforcement, right?
Correct.
All right.
If that was the question.
Yeah.
If not, let him. He can ask some more, and we'll catch it.
Yeah. So you also showed a lot of case studies about strengthening of existing structures. Now, a couple of questions that I actually saw is that once you're actually putting or modeling these strengthening requirements, what is happening in the foundation of the structure? Do you actually model the foundations? Do you strengthen them?
Absolutely. There's scenarios where if you get to the point where you're doing multiple floors, adding live load, it's a load path thing. You may have to increase the columns, right? That added load may increase issues. You know, now you have a building made with seismic, and then it all gets down to the foundation. There's many projects where our strengthening starts literally at digging out the foundations and making the foundations bigger, and the columns and all the stuff above.
Okay. And another question talks about shear deficiencies in beams. Let's assume that you have a partial shear deficiency in a beam. Do you recommend to actually only strengthen the part that is deficient, or do you actually recommend strengthening the full span of the beam?
Regarding shear?
Yeah. Yeah,
regarding shear, typically the shear demand as you get out towards the center drops off. So most of the shear strengthening we've done are basically at the ends. I have seen them where the deficiency was all the way through, but it just depends on what the existing capacity is. But usually it's just at the ends. And I should have mentioned just to give an overview of in what Tarek mentioned in his FRP scenario when he told you all those limits. With FRP, flexure ultimate capacity increase is about 40%, and you start bumping into all the limitations that he talked about. Now, and the other variable that is how stiff is the slab or the beam. The stiffer it is, the less effective the fiber is going to be, because how much strain can we get in the bottom of the fiber. But in certain slabs, you can stay in that range, that 40% increase in ultimate range, and sometimes double the capacity. So 30 to 40%, say in flexure. In shear, FRP is about 50%. Assuming you got enough depth, you probably need about 300 millimeters minimum depth to develop that U-wrap. And in confinement is only about 10 to 20. And round columns are maybe get 20, square columns maybe 10 because of the geometry. Those limitations, I should have said that at the end, are what take us into these more elaborate conventional type scenarios.
Okay. Next question asks about, so you've talked about the placement method of the form and pump. For overhead application, what's your take on form and pour instead of form and pump? And if somebody actually decides to go for the form and pour for whatever reason, what are some of the things that they have to consider
Yeah, good question. So I have this slide up. If you pour from the top and you can pressurize it, great. The problem with pouring it from the top is there is zero, let me get my laser. There is zero intimate contact at this surface, right? And the other nice thing about when we're pumping it from the bottom to those vents, we're pumping the bleed water out, that bleed and fines out. This, you can't do it in this format. So without intimate force, if you pour material in there, you can't create a pressure head or pressure, pressure head from the material. It's not going to bond. You're going to have a cold joint. And the odd thing is, people that don't know form and pump want to do this because it seems simple. It takes me the same amount of time to pump into that form as it does somebody pumping material into this void here. There is zero change in dollars of the actual placement. The only difference is I take about 5 more minutes to pressurize it versus pouring it, and I have to put a couple whalers on the form and make it a little bit stronger, which is minimal. There's not that much difference in this. And I would say to you that if you want somebody to do that and they're so convinced they can do it, make them do a mock-up, core it, and pull it. I'll guarantee you, because I've made that challenge and I've seen it done before. You would core through this slab right here if it wasn't bonded, and when you pulled that core bit out, the core would fall out. Because you always do mock-ups. I'll show you a mock-up with form and pump, and somebody show you a mock-up with pour. I guarantee you have different results. Good question.
Interesting. All right. You've also talked about concrete repairs, and you've showed a figure of or some charts that you need to make your shape some sort of regular shape or rectilinear shape.
Yes, rectilinear, yes.
Can you go back to that slide? I mean, the question says that they missed this slide and they just want to have some more clarity. So if you can just summarize it again.
Yeah, sure. So if I have like this, I showed this shear wall. This is the end of the shear wall, the boundary condition. When you start chipping this out, it looks like this when you chip it out to the left. You just chip the bad spots out and you start squaring them off. Because the other thing you have to do when you do a repair is you're not only just chipping air out. You saw cut down a minimum of say 12 millimeters to make it square, and you make it a uniform depth. So you want uniform rectilinear and uniform depth. Now, the idea is you pour this back like this, you're going to get all kinds of reentrant cracks and things like that. So what they say is take this shape, and instead of all this saw cutting going around here, just make it rectilinear. Make it this kind of upside down L shape, which is this shape squared off to do that. And on this picture I showed here, that if you tried to place if you put a form over that and pump concrete and get in it, you're going to have all kinds of problems. So the idea is square it off, take these red areas out and square it off, and then get to that shape to the right here with this rectilinear. And it should be rectilinear, and it should be uniform in depth too, and it should have 90-degree saw cut and chip down 90-degree in all these edges.
All right, next question talks about inverted panels or shear caps. So the question says is, how can you ensure that the top reinforcement has the development length required for resisting hugging moments, especially if you have a small shear cap?
If I was talking about, it says the existing steel and the slab above, that's what it sounds like?
I think it's for the new steel for the shear cap that you're using. How do you make sure that it has enough development length required to resist the hugging moment?
Well, if it's just a shear cap, it's just getting designed for punching shear. It's going to go out, so I get to that. It's got to be long enough to get me past that shear perimeter. So I go to Dr. Turek, and he sits down, and those guys calculate the length it has to be to get out for that column, for the demand of that column for punching shear, that it's past that shear perimeter plus development length. That's just all in the design.
Again, and with the last question is what do you think is the best way to strengthen a conventional RC slab if you have any issues with deflection?
Great question. So carbon fiber is probably your last choice. Unfortunately, you think I could, even if I lifted the slab up which is something that's not easy to do because sometimes you make trouble doing that. I lift the slab up, I put fiber on. I'm going to increase its capacity, but I haven't changed its section properties any. Fiber is as thick as a couple credit cards, so it doesn't add much stiffness to the element. So I can do the same thing. I can lift it up and put steel plates on there, right? They're going to be a little better. I can lift it up. I can lift it up and put a concrete section or a beam under it, right? Or I could like the slabs I showed you that were deflected. I could put, if I don't have dimensional up top, I could put a thin bonded overlay on that thing, level it off, and design that overlay so that I don't increase I increase its capacity so it doesn't deflect even more.
All right, Jay, thank you.
FRP, unfortunately, is not the best one, although it'd be the easiest.
All right, Jay, thank you so much. I want to thank everyone again, and you guys have a good evening. Be safe, and
Be safe.
Yeah, you too. Thank you.